Welcome to the Coherence Times, where we dive into the science and the story of quantum computing. I'm your host, Ryan Mandelbaum. Every other week, I sit down with researchers, technologists, and thought leaders to unravel the incredible challenges and breakthroughs that are shaping this generational technology. So, whether you're a tech enthusiast, an industry leader, or just somebody who's curious about how quantum computing might change the world, you've come to the right place. So together, we'll demystify the concepts, bust the myths, and explore not just how quantum computing works, but how it can work for you. This season, we've been speaking a lot about what quantum is and its nuts and bolts underlying how it works. And we've also started to talk about how people actually expect to use quantum computers. But maybe we've left just a little bit of an elephant in the room. And that's, when will quantum computers actually outperform classical computers? So for our last episode of the season, I'll be speaking with Abhinav Kandala, who is an experimental physicist at IBM Quantum, who currently leads the quantum capabilities and demonstrations team. Abhinav has been working hard with his team to find validated demonstrations of quantum advantage, or as we'll get into, places where quantum beats classical computing alone. So let's dive right in. Hey Abhinav, how's it going?
Hey Ryan.
Awesome. So why don't you tell me a bit about how you got into this is such a specific thing. How'd you get into it?
I joined IBM about 10 years ago after my PhD. I was working on in experimental condensed matter physics, playing around with these cold fridges that we have. Was doing a lot of nanofabrication, which is the kind of tools that we use to build our qubits. And there were certain skills and certain tools that I wanted to learn. IBM was kind enough to let me come and learn these as a postdoc. Some of our very first experiments here are beginning to explore what can one do with a quantum computer. So this was even before we necessarily deployed a quantum system online, even with existing internal devices. We were beginning to think about, okay, what could one do with this if one wanted to potentially study the molecular properties of some small systems. It was a very complicated experiment for that time. Results we got should have been very discouraging for what the potential of these systems could have been. But it motivated us even further to ask, hey, are there other tricks that one could come up with to actually extract useful information from these existing noisy devices, even at a small scale? And basically led to Kristen, Sergey, and Jay inventing error mitigation here at IBM. And then, the next several years were, taking those ideas and trying to get them to work in practice, trying to show this on small scales. Along the way, I was also very interested in trying to understand a lot more about the hardware, trying to understand how furthering my understanding of the hardware could help drive where these demonstrations could actually go. So can you actually leverage knowledge of the gates, of measurement to do even more impactful things from these devices and really milk out every little ounce of performance you can get from these?
So basically in the earliest days, we don't even have Qiskit yet, right? You're just, we have these chips and we have to basically almost hard code them to use these experiments that we're building in order to run, basically to store quantum information, manipulate quantum information.
Right.
And then, in the sort of interim, and you're just trying to figure out how do we get better and better results out of these noisy devices with these tools like your error mitigation,
Exactly. And so all of this was a very organic evolution of the software, the method development itself, like these error mitigation tools, the hardware. All of them were kind of going hand in glove, and they all, over the course of the last 10 years have kind of merged into enabling the kind of things, we can begin to do now, on the scale of, a few tens to 100 qubits, potentially pushing beyond what one can do with state-of-the-art classical methods alone.
So we're going to talk a lot about what we can do now, but I think we'll need to define a core term that we're going to be talking about a lot today, which is just what is quantum advantage?
So the first part is, I guess, quite easy, and I think people understand that you want you want quantum hardware to perform a task where you have a separation over classical only methods, and and what that means is that you're able to perform this task more efficiently or cheaper or more accurately than using a classical algorithm computer alone. The second piece, which is perhaps a little forgotten, and that's why I want to emphasize this a little more, is the validation piece, is also rigorously validating that the output from your quantum computer is correct, is trustworthy, and this even goes, quantum advantage is such a controversial, but also, it's a kind of term that really gets people going. But even if you take a step back and you want to, ask about how do people compare classical methods,
Right.
like even you have one problem, and there could be 5 different classical methods to address the same problem. How do you determine if one of those 5 has an advantage over the others?
Right.
Right? You have to ask, well, okay, did you get a better solution in terms of more accuracy? Was there shorter runtime to solution? Was it cheaper in terms of resources used? Right? But also, do you trust the solution that you got? Right? And all of this gets very nuanced and complicated because you often get into a space where there doesn't exist a knowledge of what the exact true answer is.
Got it. So basically, I mean, with quantum, we're truly entering this space where we're running calculations that we don't know what the correct answer is, even with a classical computer, for at least to get the exact answer out.
Exactly.
Got it.
And I mean, and this has been the state of even what one could do with classical simulation for decades, right? I mean, they've really, built a system of trying to build trust in what classical solutions, or classical approximations produce in the absence of an exact classical result, right? Or an exact result. And so it's the same process. Now you have a new paradigm of computing, you have a new computational tool. How do you establish trust in that new computational tool? It just turns out it happens to be a quantum computer now, but it's really asking the same questions again and again.
Are there tools that are from, I mean, yes, like you said, something that, we've been trying to make better and better classical computing for a while and introducing these new hardware, new methods, things like that. Are there tools from classical computing that we're sort of porting over to try and establish that quantum is better than classical, kind of in this rigorous way?
It's not even a matter of pitting one against the other. There are tools that are being developed in classical that we're actually leveraging to further what one can do with quantum. So this also gets back to a misunderstanding that some people have often in viewing quantum advantages, a battle of quantum versus classical.
Right.
One can absolutely have a demonstration of quantum advantage where one actually ties in quantum with perhaps very heavy duty classical resources as well, to outperform what one could do with classical alone. Right, and this is this is perhaps perhaps even more likely to happen because you can have part of the workload being shared by classical where those computers and algorithms are really good at doing part of the job, and then the quantum can do the rest.
This is almost something we've seen like when GPUs came on the scene too, right? We always talk about these price performance trade-offs, and it's almost like now we have to think about the exact same thing happening with quantum computers.
Yes, absolutely.
Before we move on, I wanted to actually ask, well, first off, I think that a lot of, when I hear the word quantum advantage, the first thing I think is, oh, like quantum's, it's time, we've rolled it out and it's doing things that are useful. But indeed, I actually don't think that quantum advantage immediately implies useful, right? Can you get into that?
Yeah, it's certainly not a kind of phrasing that I personally like to get into because useful, I find to be a very relative kind of phrase.
Oh, we've reiterated on the podcast over and over again that like it's been useful for physicists for like a long time.
Yes,
so useful.
Exactly. And then whether something is useful or not can even come up later on, right? Like I mean, you might execute a circuit and show separation in performance of that circuit between quantum and classical today, and then 3 years later, someone determines that particular circuit is exactly what enables an advance in finance or in chemistry, and so this is such a relative. It has a different meaning for so many different people, but also this is something that you can't establish at a particular point in time. So I I'd much rather focus on examples of problems, examples of circuits where one can establish separation with classical alone, and also demonstrate that those problems, those circuits can be executed on the quantum device with trustworthy validated solutions.
Right, you're a physicist or a computer scientist slash physicist slash engineer slash mathematician, whatever you are. And so it's not about like, oh, I'm going to go off and make $1 jillion with what I'm doing right now. The thing that really is exciting to you, if I'm getting this right, is just like, this is like a rigorous demonstration of quantum outperforming classical alone.
Right. I mean, I would like to make those $1 jillion as well.
Yeah.
But the second part is also very exciting.
But why does that part excite you? That's really cool to me.
Yeah, I mean, because it's really these are very significant moments in the history of computing, right? Like what are the kind of tasks we can run, we can execute, computing things very differently using a very different technology, and also personally for me, it's technology that's being built so close to very fundamental science discoveries, and that trajectory is often it spans decades, but particularly in this field, we've seen that to be so such an accelerated timescale between where work of this flavor was just an academic effort, was just about publishing papers, and now we're actually talking of a computational tool that people can use without having any idea of what the fundamental physics is, that actually enabled building these things.
Right, a bunch of physicists are working for a computer science company, making computers.
Exactly, exactly, right?
And it is really cool because, and this is kind of tying that in, is like, every time you make a bigger demonstration of quantum, like, it's not just that you're doing something new and interesting, it's like you're doing something that like scientifically has not been done before. Like you're actually breaking new ground with some of these circuits.
Right, absolutely. And even within the field of quantum computing, right? I think another really exciting piece of all of this is for me, for the longest time, people didn't think that one could do anything trustworthy, accurate, useful before there was a device that is fault tolerant, right? And we've been really pushing that thinking, right? And saying that no, even with pre-fault tolerant devices, there could be utility. There could be things that one could do which are accurate, trustworthy, and still very challenging for classical computation. And this even within the field of quantum computing, has been kind of against traditional thinking. And it's been really amazing to see the increasing number of people embrace this, try these things out for themselves and begin to explore what one can do with even existing devices.
And we're sort of at almost like an inflection point right now, right? Can you get into like, why is it that now is such an exciting time for this search?
Maybe the first thing to say is, we spoke about the absence of an exact solution classically, right? For many problems. And this comes down to, in very simple terms, how large a matrix can you store on a supercomputer?
How many numbers can you compute with at the same time?
Exactly, right? And so if you were at the boundary of like 55 to 60 qubits, for instance, trying to represent that state on one of the world's leading supercomputers using all the memory, that begins to get impossible.
You need 2 to that number.
Exactly.
Yeah.
Exactly, right? So if, for instance, you were at a 30 qubit scale or a 40 qubit scale or even approaching the 50 qubit scale, one could imagine that you could have done this kind of brute force classical computation to produce the result. So one could ask, well, why even have a quantum computer, right? So the first thing that needed to happen was you needed quantum computers to get beyond the scale. And that's what we mean by utility scale, right? Like we have systems now with 100 plus qubits, and these are well beyond what one can do with brute force classical computation, right? And then the second piece of this is you need them to be able to perform computations accurately, right? So it means that you don't want there to be too many errors. Yes, one can, if we understand the noise, we can manipulate it in ways to undo its effect, but this comes at a price which has an exponential dependence on what the error rates are. Right? Over the last 2 years, we were at median error rates of about 1% on our systems. Now we're close to 0.1%, which is actually huge.
Right.
Like the 10x might not seem that dramatic, but because of like how exponentially sensitive you are to these error rates, it has tremendous implications for the kind of computations you can do, the accuracy of the computations you can execute. And so this particularly, so the improvement in scale, when the quantum experience came out, we were at 5 qubits.
Right now it's
anything that could run on 5 qubits, you could perhaps do on your phone, right? So it was critical to get to 100 plus qubits. It was critical to be able to get to that scale while dropping the error rates, while improving the quality, and also then aspects of speed. Being able to run many circuits extremely fast is also a very crucial part of all of this. So all of this had to come together, and it's now at this point where we're able to execute circuits at this few thousand gates, at this 5K level, if you've heard this in the past, where things can get challenging for state-of-the-art classical methods, and your quantum device is able to produce accurate solutions.
Awesome. And so one thing, like, we're talking about there being better, but I think the undercurrent here is like actually having some sort of rigorous demonstration that they're better. So how do you rigorously show that quantum plus classical is outperforming classical alone for something?
This is a great question. And so for this, we've tried to bucket our different approaches towards quantum advantage, in 3 different ways. And each of these gives you the ability to validate rigorously what the solution is. Okay, so maybe the simplest one to start with are problems with efficient classical verification, in which the circuit or the problem is engineered in a way where perhaps you already knew what the actual result is. So there is a known answer to compare to, right? So you know what the answer is. The person who creates the problem knows what the answer is. But if you didn't provide the answer, and you asked either classical simulation folks or quantum experimentalists to try and find out the answer, are they able to do it, right? And then there's a potential competition between the two. And then because you know what the answer is, there is that benchmark to compare against.
Factoring is like the best example of this. I mean, it's not what we're doing right now, but
Yes,
that's,
exactly.
We know that factoring is really hard. So 2 methods that compare, you know that the one that gets to the answer faster, you already know, you multiply it together, you check the answer.
Exactly,
right.
Exactly. That's the classic example, right? And then examples of things where we're trying right now are, for instance, what are called peaked circuits, right? And these are basically, trying to run random circuits where it's known that where the circuits are engineered in a way that the output has perhaps one bit string that really dominates the output distribution. And this is really a method that was, this was an approach that was proposed by Scott Aronson to try and solve the verifiability problem of just traditional random circuit sampling.
Right. So a previous way that we were trying to demonstrate these games were like, we do have a random circuit. Just a quantum circuit is basically doing random things. And then from that, that there's some amount of, you can kind of figure out what the most likely answers are. But this one is, there's actually a most likely answer that you can kind of inject into the whole thing.
Right. And then you can ask, is my quantum computer able to find that particular peak, or that most likely
string of bits?
Is my classical simulation method able to do this? And then you can basically compare the two, right? And so this is nice because these are problems where there is this flavor of efficient classical verification, right? Now, 2 are problems with variational solutions, and what I mean by that is, one flavor of tasks that people hope to run on quantum computers are trying to find ground states, so the lowest energy states of different systems.
Right, and this is like holy grail. Like quantum would be really good if it could find the ground states.
Absolutely. I mean, this has been one of like the original motivations of even building a quantum computer.
Right.
You build a quantum computer to simulate and predict what other quantum systems could do, and you want to do this where classical systems can't, right? So the nice thing with variational solutions is that if you get a result from either a classical method or a quantum method, you know that result places an upper bound on what that lowest energy is.
Got it.
Of that system. And what I mean by upper bound is that energy can't be larger than that. So what that provides you then is an ability to rank solutions. If you produced a lower energy than all previous methods, it means now you have a tighter upper bound.
This might actually be something that's misunderstood, right? Is that it's actually incredibly hard to exactly calculate the ground state. It's like one of the hardest things you can do with a computer.
Exactly.
But we have these quantum methods that are really good at approximating it. And so for this, because we know there is an exact answer that's really hard to get, it's just we can go with these approximations and get closer and closer and closer, right? And then it makes sense that the lowest one wins.
Exactly. That's another example of trying to establish confidence in the result and make a statement of, okay, we got the lowest energy, presumably from a quantum device, that a classical only variational method could not produce. So this is the second bucket. The third bucket comes to observable estimations, which is basically trying to measure often properties of the state, for instance, in quantum simulation. You have a bunch of magnets that are interacting, and you turn on some interactions, and you want to study how the magnet, the net magnet of this interacting system, how does that evolve? How does the net magnetization of this?
Yeah, and this one almost can be treated in a oversimplified way as like a weighted average almost.
Exactly.
Yeah.
Yes. Right. An average of
system.
Yes, an average of the individual spins. And here you're going to ask questions like, okay, how does this property evolve over time, or how does this property evolve as I turn on a particular interaction? Questions like this, which are very relevant in quantum simulation.
Well, if you have like a bunch of coins and let's say the coin can be one value 0 and one value 1, then you'd eventually, if you're flipping like a lot of them, then in some system you'd have some average between 0 and 1, like 0.5, and then you could introduce fields to sort of get that number to change.
Exactly. Yeah, that's a nice, simple way of looking at it. And so. These are the kind of tasks one often does in a number of algorithms that people hope to run, particularly in the near term. Mm-hmm. Okay, because these are also the kind of quantities that typically error mitigation methods can really help recover. Mm-hmm. Where even in the absence of fault tolerance, you can be preparing states that are very noisy, that have very low fidelity. But still, you can extract properties of that state, like these averaged quantities, which are very accurate and which are noise-free.
We didn't actually get into this enough, and maybe we'll take a second to talk about it, but this error mitigation is actually quite a large deal for being able to do things in the near term. These techniques that allow you to look at the noise of a system and then essentially do the same thing that like noise-canceling headphones do, or even just extrapolate to what it looks like with no noise to have one of these averages emerge.
Exactly. And have these averages emerge in a trustworthy, accurate.
Right.
That's the key of
this. Is actually the hardest one to understand. I think the first two are really clear what they mean, but this one, so we actually have a way to establish like a rigorous sort of boundary within which a right answer has to fall, right?
That's precisely the goal, right? That's precisely the goal. And yeah, so there are, when you have experimental signal that is noisy, that's non-ideal, there are a whole bunch of things one can do with that signal, in post-processing to try and boost it or try and, estimate what you think the noise-free value is. But then it's very important to ask how many of those post-processing methods or how many of those techniques that one wants to use enable you to track the error you're accumulating, as you make assumptions, as you use different kinds of tools, right? So yes, you want to produce a number that represents your estimation of that particular observable, that particular average. But can you also place error bars on that, which give you confidence that the answer lies within this boundary?
Mm-hmm. And these are not coming from the quantum computer. They're coming from our kind of overall knowledge of the problem and,
No, well, they can come from the quantum computer as well.
Okay.
They can come from the particular error mitigation method as well.
Got it.
But essentially, you want to have trust in all the methods that you employed to get the solution.
So maybe a better way of saying it is, like, for me at least, is that there's an independent method to establish this boundary in which the right answer has to fall.
Right.
And then once you've independently established this sort of boundary, then you can try out your different methods and then do your little, classical only versus classical plus quantum and see which one falls within this boundary and which one doesn't.
Yes. And I wouldn't say it's entirely independent. I'd say that the process of the computation gives you a sense of what that boundary is.
Got it.
Right? It's you're using methods that enable you to place rigorous error bounds. You're then able to compare to all other methods and say, okay, well, are these results coming, within this boundary? Are they outside? So on and so forth. And then you can compare runtimes and things like that.
So with all these different methods, like, how did they arise? Has the community kind of been all working together, or specific groups making them up? Like, how are these different all these different circuits coming about?
The variational methods have existed for a very long time. They've existed, even in classical. And there was an algorithm that was that was proposed in the maybe 2010, 2015, that time span, where people showed that you could extend these ideas even to a quantum computer. Error mitigation as an idea is also perhaps 9 or 10 years old, and that's really enabled the operator estimation piece, trying to measure observable estimation piece, trying to measure observables with rigorous error bounds. This has absolutely been, a community-wide effort. I say this often. We're experts in building quantum computers and figuring out how to extract useful information from these, how to manage errors, and so on. But really, there's an entire community of experts from different fields who know what are the problems that are challenging for them to execute on classical alone, and that input has to come in.
We talked about how now really is starting to become the time that quantum is, beginning to be competitive with classical. So in these three different regimes of validation that we're talking about, how close are we?
That's another great question.
It's a big question.
Yeah. So once again, it ties to something that I just said, which is I'd consider myself an expert in trying to build a quantum computer, trying to figure out how to use it, but not in knowing what the classical state of the art is. Right, and so if you think of a typical collaboration on a project of this kind, it would involve either someone from the external community saying, hey, we think there's a proposal for a quantum advantage because we are experts in this particular field and we know all the classical methods that have been used, and we know what the classical state of the art is, and let's try this. Or it could involve, like for us, approaching another classical group saying, hey, we've been able to execute these circuits really well. Can you help us benchmark our experiment? Can you help us, can you tell us what the classical state of the art is?
So this is actually interesting, right? Because on the one side, you have these folks who are already using classical state-of-the-art methods that they think are really good.
Right.
And you sort of come in with like this quantum sledgehammer and say, oh, actually, I think we got something that beats that. But then we don't actually know if that classical method is very good, is the best yet, even if you give a better quantum solution.
Right, exactly. You'll very quickly discover that what state-of-the-art is, it has different meaning for different people in the community, right? Yeah. And this is played out so many times, in our internal, in our collaborations, say internally or even with external classical simulation folks. It's also played out, when you see high impact prominent papers on the archive, and then there'll be like this.
It feels really good for quantum to come out and say, I did it, and then you say, oh, I ran that on my laptop.
Yes, exactly. And I'm very familiar with that. A big part of this was, are there well benchmarked problems where everyone accepts that, that this is the best classical method, this is the result to try and outperform, or is there a way to speed things up, beyond this kind of, small research collaboration, where you can essentially open things up for anyone to contribute to the project, right? For anyone to be able to tell you that, hey, I have a new classical solution. That's better and amazing. If that outperforms whatever whatever you ran on the quantum device. Terrific, great. Science has moved in the right direction.
Computing, you found a better way to do a compute problem.
Exactly, terrific. And you're enabling us to zero in on what are the examples of circuits or problems or parameters where there could be a solution, right? And the nature of all of these different classical methods, is that there are approximate methods, and they work in certain regimes, and they don't work in certain regimes, right? And so every time you have a new classical algorithm come in as well, it's also teaching you about what are the kind of parameters where there's this new state-of-the-art method doesn't work, and that also gives you now a new example to try with your quantum device, for instance.
Got it.
So this is exactly how science should progress, and coming back to your question, it can only be a community effort to be able to determine if things have been rigorously checked, and once again, and what it also implies, even though I haven't said it this way yet, is that it can't be a single moment in time that one announces quantum advantage. It really has to be this community-led validation of like, okay, yes, we trust the quantum solution, for instance, or within whatever bounds you can place, and then some community-driven classical benchmarking of the problem as well, where different groups, from anywhere in the world can try all their favorite classical algorithms and say, if this is the result we got, this is the kind of runtime we require to get to the solution, these are the kind of classical resources, this is how much it cost maybe.
Right. So this really is this level of, I think what it sounds like to me is that these three kind of different categories means that you're trying to almost wrangle the troops around a certain set of problems, because if everybody kind of agrees on these as being the three different ways to validate, and then starts digging into publishing results in these three different categories, then it really helps focus the field around these, so that there isn't somebody at some mega super compute organization who just hasn't been paying attention and then shows up and kind of is like, oh, I actually did that in 20 seconds. But kind of like the more you can get the community riled up around these things, then the better chance you have that you actually will have one of these advantages emerge and then actually stay an advantage for a while.
Right. And it doesn't even, necessarily need to be, people don't necessarily need to be riled up, right? I mean, they could even, they could even think of coming up with their own proposals for what could be a potential place for advantage. And eventually what I would really love for this to be is, once again, for really everyone to realize that with quantum and classical together, we're moving in the direction of a new computational tool rather than pit quantum and classical against each other, right? And this is what we often mean when we talk of quantum-centric supercomputing as a platform of using the best of classical, the best of quantum to perform new computational tasks that we couldn't have with classical alone.
We'll definitely get a bit more into that, but I wanted to first get a bit into these specific things, because we already kind of talked about the utility and usefulness about quantum computing, and about sort of that they're already doing things classical computing can't do. But it's more like there's computations that, we'll say useful or like relevant computations that quantum computers are in the midst of trying to outperform classical on, right? Do those circuits, these problems that we're using to benchmark these, is there sort of an imagined route to making those useful? Basically, all I'm saying is like, we have these three awesome ways to benchmark quantum circuits against classical only methods. When do those, are those eventually going to provide value too?
Right, exactly. So that's exactly the essence of this path, right? Of first trying to establish classes of problems and circuits where we have carefully validated the quantum solution and benchmarked against state-of-the-art classical methods, done with the community. And once you have those examples, that could motivate, for instance, research into how do these kinds of circuits connect to problems I care about in my area of expertise. Right?
My airplane routing problem looks exactly like this peaked circuit problem you were talking about, and then easy peasy, I can almost have this verified thing to start building.
Right, exactly. And so this is certainly one way to find advantage for particular use cases. There could be more empirical ways as well. That one could hunt for this, and we should be open for happy surprises. as with most of science. But yeah, this is exactly what we hope. Identifying catalogs of circuits that have been rigorously tested on both quantum classical, and then using that to motivate how does this connect to a particular use case.
How are you catalyzing? You're actually doing some work to try and catalyze the community around finding these and extending these advantages, right?
Right. No, absolutely. And I think maybe a month ago or so, we launched what's called the Quantum Advantage Tracker. And this has been tremendously exciting, and it's a very different way of doing science. Experimental physicists often have what's called a lab notebook, where they kind of, they write down, okay, I came into the lab today, I did this was my hypothesis which I wanted to test, and this is what came up. And usually these lab notebooks, just stay inside the lab.
Right.
No one ever gets to see it. Maybe you get to see it if someone wins the Nobel Prize and you want to go back in history and see like what did they write when they first saw the discovery for the first time in their notebook, right? What the external community gets to see is a research paper, which is the culmination of many pages, or many days or weeks or months of lab notebook writing.
Right.
And we're almost getting a bit of openness to that process now, right? Where in real time, we are essentially updating, for the world to see results from quantum and classical groups emerge, right? So just yesterday, we had an entry into this public community-driven quantum advantage tracker, which was an experimental result that was basically a day old. And this really, is going to accelerate this process. One, it makes it completely open. Anyone can view the data. Anyone can submit an entry in these different classes of problems. Anyone can keep track of what's going on. People can propose new circuits. People can propose new methods. So, for instance, even for us, there's such a big growing family of error mitigation methods. For instance, to make this example a little more concrete. So, say we have a circuit we have benchmarked classically, and we think that this particular circuit really is challenging many state-of-the-art classical methods. And we want to test this performance out. So maybe today, I want to go and try this particular circuit with error mitigation method A. Okay, then 2 days later, I want to try this with error mitigation B, right? In the traditional way of doing science, you might wait till all of these methods are tested, and then you want some you want to report this in a paper that's going to take weeks and months to put down, and then goes through peer review, or it might be on the archive. But this is a very long process.
Each of those methods is going to be a paragraph in a science paper.
Exactly. Instead, if I've tried method A, can I report it publicly today?
Yeah.
If I write method B, if I run method B, can I report it to the external community next week? Right? This really accelerates things. Now, in the meantime, a classical simulation group comes along and says, hey, this particular circuit you thought was really good, well, I can simulate that on my laptop, right? Great, we've learned. So now we start trying things on the next classical circuit, right? On the next quantum circuit, which perhaps, has changed some parameters, some aspects of the problem to make it challenging even for the new classical simulation algorithm. So all of this, really, I hope moves in the direction of accelerating this feedback loop tremendously, breaking boundaries where you aren't limited to just a limited set of groups, but anyone in the world can contribute on the quantum side, on the classical side. And it just moves science, much faster than, it otherwise would in the traditional sense.
Yeah, I mean, it's actually kind of beautiful if you think about it, right? Because it is, you said that it's very different than traditional science, but it's actually the definition of traditional science. Like, we have 3 hypotheses, right? The hypothesis is that quantum is better than classical for these 3 different techniques. And then, what do you do when you have a hypothesis? So scientists all try and either prove or disprove the hypothesis. So us quantum folks are coming out with better and better programs that can, say, yes, look, quantum is better. And then, as is typical with science, you also have people who are running the same tests trying to falsify the hypothesis. Unfortunately, I feel like a lot of people don't know the scientific method in its purest form, but the purest form is really like, I hypothesize this thing is true, and then I now have to try and prove it false a lot. And it's like, we're all now, instead of us in the lab trying to prove it false, and then publishing one time we tried proving it false, it's like, everybody at the same time is all trying to prove these hypotheses false, and then the quantum advantage emerges as a sort of beautiful flower that, okay, we all tried to prove it false, and the last person, it's been a really long time, we're all trying, and now it seems like quantum stayed ahead at the end of this all.
And it's really exciting. I think, already we have probably 10 institutions that are contributing to this in less than a month. And I'm really hopeful and confident that this number will grow, and it'll really become something that the whole community embraces. And yeah, as you said, there's really no shame in one method beating another. It's really like this is all moving science forward. And just as I think a couple of weeks ago, we had a posting of a quantum experiment, the results from that. And then, there was a posting from, I think, the University of Wisconsin-Madison saying, hey, we get better energies than your quantum result. Great, and this is something, that we're incredibly proud that, people are beginning to use this tracker in this way, where we learned about your method, much faster, perhaps than we otherwise would have. And everyone begins to contribute and learn, at a much accelerated pace.
Awesome. And so now this is the question that I'm really excited about, because we always talk about quantum advantage as this major milestone. It almost feels like the finish line of quantum computing. But in the paradigm you're setting up here, once you hit quantum advantage, you actually just have a bunch of really interesting circuits that we know are like quantum better. But we don't actually have this sort of explosion of quantum killer apps. And so, then the question kind of remains of okay, well, once we have these quantum advantages emerge, then what?
So once again, it's a matter of scale and gate count. Where we're talking of examples of quantum advantage emerge, at the 5,000 to 10,000 2-qubit gate level, 5,000 to 10,000 2-qubit gate operation level, right? But there are many, well-known classical algorithms or well-known quantum algorithms that would require, say, millions of gates or billions of gates, and going in that direction of being able to execute so many of those gates is really our path towards fault tolerance, right? So what we're hoping to learn in the near term or in the immediate future are what are those examples of circuits problems that I really would love to see use cases being mapped onto already at this kind of scale, which already we see are examples of computations that are challenging for classical alone, and then it's really filling those spaces as we go along, right? The path towards building more powerful quantum computers, the path towards fault tolerance is essentially going to take us from a regime where we can execute circuits from a few thousands of gates to millions and billions of gates. And then there'll be different use cases which will apply for every era almost of this journey.
And then the thing we're not really talking about, but you brought it up before, is, I think maybe having had this conversation, people still might feel a little bit like it's quantum versus classical. But when these quantum methods are succeeding and being extended, often there's a classical HPC workhorse that's helping it succeed. So it's the classical HPC cannot do it alone, but the little quantum that could combine with the classical HPC is now kind of giving it wings to fly. So it seems like that's going to really be a big piece of it too.
Absolutely. And we're seeing so many examples of this. Ground state energy calculations that I was alluding to on quantum computers for fairly large complex physical systems, but they're only being run on these quantum computers today because there's a classical HPC piece that's working in tandem.
Right.
And we'll see many more examples of this kind of work where it'll almost be fairly obvious that this is the future of computing.
I mean, then it's literally, it's goes full circle here. It's literally this GPU, CPU versus QPU, CPU price performance trade-off. It's all about how much quantum do I need to make it cheaper to run it on a quantum plus classical than classical alone, which is already, people are so familiar with this idea if you've ever used, a GPU when you're doing calculations.
Right, and I think here you'll probably see examples very soon where it's not even a matter of just price performance. It'll be examples of it would have been impossible to do this on classical alone. The only way to do this was because you were able to integrate a quantum piece inside inside your traditional CPU GPU space.
Awesome. So I wanted to start wrapping up. This has been a really fun conversation, but I had, first off, maybe is just, what would you suggest somebody, I mean, really this has been a community call to action. You want people who are gonna come in and on both the quantum and classical and then classical alone side, just try and break this, try and figure out how to do this in a way that just try and basically get quantum advantage to emerge from this mess. So what would you recommend to somebody who's getting excited about this?
So it depends on your expertise, I guess. If you're a domain expert, really educating all of us on what are those problems that are really challenging in your area of expertise that could potentially be mapped onto these kinds of circuits of 5 to 10,000 gates. That's really, we need the domain experts to be telling us that.
Like the guys and gals who do computing at the plane companies and train companies and candy companies, just like, if you have a problem that's really hard, we won't know if it's good for these circuits until you show it to us.
Exactly, right? Certainly the classical simulation experts, to also help, drive our collective understanding of where are those regimes where some of these state-of-the-art methods fail. I think that's a very natural entry point. I'm quite optimistic that this will grow to be an effort that everyone from universities, national labs, industry, even some of our hardware competitors, even really embrace is a path to collectively understand what is a rigorously validated quantum result, what is a rigorously benchmarked classical solution, and then that will drive our understanding of a credible claim of quantum advantage.
Cool. Well, if you're optimistic, then I'm optimistic. So maybe I'll end with just, given this optimism, what do you hope the world with fully realized quantum computing will be like?
As I said, one of the really fascinating things here in this field for me was, the very rapid transition from fundamental science to computing technology. And so I really hope that this is computing technology that performs computation, solves problems that have a positive impact on society. I would very much love for the footprint of this positive impact to happen, a lot sooner than many others imagine. I would love for, great use cases to emerge from establishing quantum advantage even at the 5 to 10,000 gate level. And yeah, I think if that happens, in particular, it'll really accelerate our ability to find examples as we go from, thousands of gates to millions and billions of gates. So I think.
Awesome. Well, cool, Abhinav. This was really fun, and I'm really glad we had you on the show. And I'm sure you will be forced to come on the show again at some point.
Great. Thanks so much. I really enjoyed our chat too.
Yeah, thank you. That's it for this episode of the Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts and share it with somebody who is curious about quantum computing. So you can find us on Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thank you for tuning in. And remember, the quantum future isn't just coming, we're building it right now.